Welcome to the Sky Commander Flight Brief. It's your mission-ready podcast for drone pilot training and aerial insights across Canada.
From Transport Canada rules to real-world drone ops, we break it down, take you higher, and help you earn your wings. Because here at skycommander.ca, we don't just fly.
It hints there's more to it. It's a masterclass, a deeper level, maybe a philosophy or a community focus, perhaps.
It's definitely intriguing, sets them apart from just, a basic tips show. Skycommander.ca is the obvious next step. Precisely. If you're thinking about flying a drone in Canada, boom, this content is aimed right at you.
Powered by skycommander.ca.
The elite podcast for Canada's drone pilot. Okay, let's get started. Welcome to the Deep Dive, the place where we take the world's most complex information and, we try to turn it into actionable, fascinating insight.
That's the goal.
And our mission today is, it's very specific, and I think it's critically important. We are going to be cutting through the jargon of the evolving low-altitude skies.
Mm-hmm.
We're going to map out the new technical requirements for beyond visual line of sight or BVLOS drone operations.
And, this isn't just about flying drones a little further away. I think that's a common misconception.
Right. It sounds like a small step.
It sounds small, but what we're really talking about is fundamentally redesigning the national airspace system, but specifically below 400 feet. We're transforming what everyone used to see as this, open, relatively free space.
Just empty air.
Exactly, empty air. And we're turning it into structured, digitally managed tunnels, invisible highways in the sky.
And this transition from that sort of open field to a managed corridor, it's not theoretical, is it? It's happening right now.
Oh, it's happening right now, which is exactly why it matters to you, to anyone listening. For the past decade, if you wanted to fly BVLOS out of the pilot site, you faced this just incredible regulatory hurdle.
The waiver process.
The dreaded waiver process. You had to petition the FAA for a customized Part 107 waiver for every single operation. You were essentially writing a bespoke risk assessment for every 10-mile stretch of pipeline you wanted to inspect.
That just sounds exhausting. And incredibly expensive.
It was both. It completely stifled scale. But the momentum is shifting, and it's shifting dramatically. The vision that's laid out in the Part 108 Notice of Proposed Rulemaking, the NPRM,
right,
it's pushing us toward routine, standardized BVLOS operations. And they're overwhelmingly focused below that 400-foot above ground level or AGL ceiling.
Okay, so the core insight here then is that once the remote pilot literally loses sight of the drone,
the moment you can't see it anymore,
the pilot's eyes can no longer carry the safety burden. You can't just, look out for other planes.
Exactly.
Yeah.
The safety case can't rest on human vision anymore.
So we have to engineer safety into the environment itself. If the pilot can't see, the system must see, and the system must manage any conflict.
That's it. That is the crux of this entire deep dive.
So today, we're going to unpack 3 foundational concepts that really define this new sky architecture. First, we have the BVLOS corridors, these invisible, pre-planned highways that structure all the traffic.
Mm-hmm.
Second, the incredibly complex geometry of what are called shelves. These are the altitude staircases that define controlled airspace boundaries. It gets tricky.
It gets really tricky there.
And third, the ultimate stress test for any operation. The unpredictable surprises. We're talking temporary flight restrictions, TFRs, pop-up traffic, you name it. Okay, let's start with the trigger mechanism. What exactly defines BVLOS? We see the acronym everywhere, but we need the precise regulatory definition because that is what automatically kicks off this whole cascade of complexity.
Absolutely. The defining statement, the one that matters, is that the remote pilot in command, the RPIC, cannot maintain continuous unaided visual contact with the unmanned aircraft throughout his flight.
Unaided, that's the key word.
That is the word the entire regulation hinges on. Unaided.
So if I'm standing on a hill and I can see my drone with my naked eye, I'm VLOS, I'm fine. But the second I have to pick up a pair of binoculars to tell which way it's facing,
You cross the line.
Or if I'm just relying on the camera feed on my screen, I'm now BVLOS.
That is exactly the plain English rule. No binoculars, no telescopes, no spotters calling out directions based on an FPV feed. If you cannot maintain that direct, continuous eyeball contact for the whole flight, you are BVLOS.
And the complexity multiplies instantly.
Instantly. Because you are now required by law to replace human visual separation with these sophisticated procedural and technical controls. It's why we have this little memory aid we like to use. BVLOS beyond vision, let out the sensors.
I like that.
You must now rely on things like detect and avoid technology, DAA, unmanned traffic management or UTM, and really robust procedural separation. The machine has to take over from the human.
And the moment we start relying on sensors and procedures, we stop thinking about a drone just flying around in an open area, and we start demanding that it sticks to a specific predefined structure.
A structure, yes.
And that structure is the corridor.
The BVLOS corridor, yes. It's an emerging concept, but it's heavily featured in all the recent Part 108 discussions. And it's defined as a specific three-dimensional volume or route where your drone is expected to operate.
And not just expected, but required.
Required to operate. And crucially, this corridor comes preloaded with standardized performance requirements and predefined deconfliction rules.
So the contrast is really stark then. If BVLOS is like flying an RC plane in an open park.
Go wherever you want, as long as you can see it.
Right. Then BVLOS is like booking a specific lane on an invisible digital highway.
Precisely. And the most important insight here, I think, is that the corridor is fundamentally a contract.
A contract. Explain that.
It's a contract between you, the operator, and the regulator, the FAA. It defines where you'll be in 3D space, when you'll be there, that's the time slot, and how precisely you'll stay in your assigned lane.
How precisely? How do you even measure that?
Well, this is where we start borrowing concepts from traditional aviation, things like required navigation performance, or RNP.
RNP.
So if your corridor contract demands, say, RNP 0.3, your drone system has to prove its ability to stay within 0.3 nautical miles of the centerline 95% of the time. It's a statistical guarantee of performance.
And this contract, it isn't just about a successful flight, right? It has to account for when things go wrong.
It's absolutely a contract about failure. I'd say that's almost its primary purpose.
Yeah.
It specifies exactly what procedures you will execute if something breaks, if a surprise pops up, or if you just drift out of bounds. The FAA is signing off on that entire plan.
And if you violate those terms,
well, the consequences can range from a mandatory automated flight termination to, potentially losing your entire operational certificate. It's a serious breach of contract.
Okay, before we dig deeper into the geometry of all this, we need a quick refresher on the structure of the sky itself. Because these corridors, they have to weave through all these existing layers. Where exactly do these ground-hugging highways live?
They almost all live in the low-altitude spectrum, primarily in what's known as Class G airspace.
Class G.
So you have this alphabet soup of airspace, A, B, C, D, E, and G. Class A is way up high, the stratosphere. B, C, E, D are those controlled cylinders and bubbles you see around major and moderate airports.
Like an upside-down wedding cake.
That's the classic analogy, yeah. And then Class E is controlled airspace pretty much everywhere else, but it often starts at 700 or maybe 1,200 feet off the ground.
So Class G is the leftover bit at the bottom.
Exactly. It's the uncontrolled airspace that's closest to the surface. And our BVLOS corridors, they typically live low below that 400 feet AGL mark, weaving through Class G, and often just skimming under or carefully navigating around those controlled layers like D, B, C, or D.
It's simpler to stay in Class G, I imagine.
Much simpler. But the trade-off is you are now 100% responsible for your own separation from any non-cooperative manned traffic. There's no air traffic controller watching out for you.
Which brings us back to this big regulatory shift that's enabling this whole architecture, the Part 108 vision. You mentioned the old world was begging for custom Part 107 waivers. What does the new Part 108 approach look like?
I mean, it's night and day in terms of efficiency and scale. The old Part 107 waiver process was so time-consuming, expensive, and just completely non-scalable. You could spend 6 months and $50,000 to get a waiver for a 30-mile corridor.
And that waiver was only good for, what, a year?
A year, maybe 2 if you were lucky, and it was operation-specific.
Meaning, if I wanted to use a different drone or fly for a different client on the exact same path, I might have to start the whole process over.
You might have to, exactly. Part 108, the vision for it, is to replace this bespoke chaos with formal, standardized pathways. It uses 2 structured approaches, permits or certificates.
Okay, permit versus certificate. What's the difference?
A permit is sort of like a fast-track version of the old waiver.
Yeah.
It's still operation-specific, but it's tied to a predefined set of rules for a certain type of corridor. The real game changer, though, is the certificate.
That sounds bigger.
It is. It grants a much broader capability. If you can prove your entire system, your drone, your UTM integration, your pilot training, your procedures, if you can prove all that can meet the RNP and safety standards for, let's say, a low-altitude infrastructure inspection certificate.
So a category of operation.
A whole category. Then you can apply that certificate to any predefined certified corridor of that type anywhere in the country, assuming it meets the same safety case.
That is a massive saving in time and cost. It's moving from, I don't know, artisanal, handcrafted approvals to industrial standardization.
It standardizes the burden of proof. That's the key. It means companies can finally invest heavily in certified aircraft and robust software systems, knowing that getting approval for a new operational area might be a matter of weeks, not 6 months or more.
And the whole framework is tied to the design of these corridors.
The entire Part 108 approval is tied directly to the robust design and the rigorous conformance monitoring of your corridor, and your absolute respect for those critical boundary lines we mentioned earlier, the shelves.
Okay, so let's unpack this. If the corridor is the invisible highway, we have to talk about the tricky geometry that dictates the ceiling of that highway. We need to talk about those steps in the sky. The shelves. The word shelf sounds almost mundane, doesn't it? But it represents one of the sneakiest, most common sources of accidental nonconformance and risk in these BVLOS operations.
Absolutely. Let's talk about airspace shelves. The sky staircase.
The sky staircase.
A shelf is simply a step. It's a segment where the floor altitude of controlled airspace changes laterally. So picture the National Airspace Map, but as a huge 3D layered structure.
Okay.
Close to a major airport, controlled Class B airspace starts right at the surface. But as you move out, say 10 or 15 miles, that controlled airspace, now it's Class E might start at 700 feet AGL, move even further out, and that Class E floor might rise again to 1,200 feet AGL.
So it's a literal staircase made of air. It's invisible to the eye, but it's absolutely real in a regulatory sense.
It is absolute. And why they matter so much is that your BVLOS corridor has to be deliberately designed relative to these shelves.
Right.
A utility inspection operator, for instance, is highly motivated to design their corridor to strictly hug below the Class E shelf. They want to stay safely in that Class G uncontrolled airspace to avoid needing mandatory ATC coordination or specific transponders.
So the corridor ceiling might be set at, say, 390 feet AGL in one section. But 10 miles down the line, if that Class E floor drops from 1,200 feet to 700 feet, the corridor itself might be forced to drop its ceiling just to maintain that safe separation buffer.
Precisely. And this is where that moment of accidental nonconformance, that slip-up, happens.
How so?
Well, imagine a BVLOS drone flying a logistics route at a steady 250 feet AGL. It's optimized for energy efficiency. Then the pilot, or maybe even the automation, decides to climb a little bit for a better line of sight signal or to clear some radio interference.
Just a small adjustment.
A minor climb, maybe 100 feet. But that small climb could accidentally punch the drone straight through a shelf floor, even one that seems far away, and now you're instantly operating unapproved and controlled airspace.
Wow. So BVLOS demands this complete commitment to planning in 4 dimensions, not just drawing a line on a map.
Yes. The 4 dimensions are completely non-negotiable for the Part 108 safety case.
Yeah.
You have to know the vertical boundary, your ceiling and floor, defined by these shelves and shielding volumes. You need the lateral boundary, the exact width of the corridor, measured in meters, not miles.
Okay.
Then the temporal boundary, when the corridor is active, respecting time of day restrictions. And finally, the relationship to ground features, the terrain, the infrastructure you're following. If you don't define all 4, that safety contract is basically void.
Let's use our CCTT checklist memory aid here. Class, corridor, traffic, time. If you ignore any one of those, and especially the class boundaries dictated by shelves, your safety case is just fundamentally broken.
It is absolutely broken. And the trickiest part of adhering to the class rules is this critical technical gotcha for low-altitude BVLOS. The AGL versus MSL trap.
The AGL versus MSL trap.
Yeah, the simple misconception for so many operators is thinking, hey, if I just stay below 400 feet AGL, I'm immune to airspace rules, I'm safe.
That 400-foot rule is so often cited as this kind of magic shield, but you're saying that shield is completely meaningless if the floor of the airspace above you is defined differently.
Exactly. The reality is that airspace shelves, the floors of Class E, C, or D, are almost always defined in MSL, which is mean sea level. That's the standard reference for manned aviation.
Okay.
But drones, especially these low-altitude ones, they typically navigate and fly at a constant AGL, up ground level, to maintain a consistent distance from the ground or the infrastructure they're inspecting.
Let's do a hard concept deep dive here, because this is where a flight can become illegal without the drone changing its programmed AGL altitude at all. This is the idea of the stacked bricks of sky.
That's a great way to put it.
Yeah.
Okay, imagine you're approved to fly a corridor at 250 feet AGL along a railway line. And this railway line runs parallel to a low mountain range.
Got it.
At the start of the route, the railway is at 1,000 feet MSL. Your drone is flying at 250 feet above that, so it's at 12,250 feet MSL. Now, controlled Class E airspace above you starts at 1,800 feet MSL.
So you have a 550-foot safety buffer. That's excellent separation.
It's great, no problems. Now, over the next 5 miles, that railway line starts a gradual climb. It gains 600 feet of elevation as it goes up a slope. Your drone is programmed to maintain 250 feet AGL, so it just follows the tracks up, maintaining that exact distance.
So if the tracks are now at 1,600 feet MSL, my drone is at 200 and 850 feet MSL.
You've just flown right into the Class E shelf that was defined at 1,800 feet MSL.
Oh, wow.
Your drone's AGL hasn't changed one bit, but you have busted the controlled airspace ceiling. You are now illegally operating in controlled airspace, potentially interfering with standard flight operations, even though your autopilot was perfectly conforming to its AGL programming.
That is such a critical failure point. It means the only practical move for robust BVLOS mission planning is that the automated system, it has to check every single point of the route.
Every point.
It has to check where the AGL altitude plus the terrain elevation is greater than the airspace floor minus some safety margin.
You absolutely cannot rely on AGL alone. You have to ingest high-fidelity terrain data, we call them digital elevation models, or DEMS, into your flight planning software. You have to correlate the drone's expected MSL altitude against those static MSL-defined airspace boundaries for the entire route.
So you have to bake the MSL safety margins into the corridor design from the start.
You have to. You have to force the drone to automatically descend in AGL if the terrain rises too sharply toward a shelf. It makes low-altitude route planning a four-dimensional chess game. It really does.
Okay, the AGL MSL trap really shows just how complex the geometry is. So now let's talk about how we mitigate that risk, especially when we're flying low and close to things. The sources talk a lot about shielding, hugging infrastructure to gain a kind of a right-of-way advantage.
Shielding is absolutely central to low-risk BVLOS deployment, especially for critical infrastructure operators, anyone inspecting power grids, rail lines, pipelines. It refers to operations conducted very, very close to structures or obstacles.
How close are we talking?
Typically within a 50 to 100-foot lateral or vertical distance, so really tight.
That sounds dangerous on the surface, but you're saying it actually makes the flight safer. How does that work?
It works because it creates a predictable, self-separating volume of air. The key regulatory insight here is something called the acceptable level of risk, or ALR. Every BVLOS operation has to prove its risk of a collision or a failure is below a certain threshold.
Okay.
When you hug a power line, you drastically lower that risk component because you ensure that manned aircraft are highly unlikely to intentionally fly within that same tight volume.
So the physical structure itself, the power line or the building, acts as a passive safety barrier. It just changes the probability of an encounter.
Exactly. It changes the probability of an encounter with manned aircraft from low to near zero. And second, it often happens over lower consequence areas. If a drone feels 10 feet above a high-tension tower in a field, the ground risk to the public is often way lower than if it fails over a crowded street.
The structure becomes a buffer.
It becomes a buffer, which is why Part 108 is moving toward giving these infrastructure-hugging corridors special, more permissive BVLOS rules. It's just easier to meet the ALR requirements.
But flying with that kind of proximity and precision, it must demand incredibly robust control systems. And that brings us to the operational control system. Unmanned traffic management, or UTM. This is basically automated air traffic control for drones, right?
That's a good way to think of it. UTM is the system that makes these long, standardized BVLOS corridors in busy airspace even feasible. I mean, without it, trying to standardize these operations would be total chaos. It provides essential services, and it's primarily focused on two things: intent sharing and strategic deconfliction.
Who provides this UTM service? Is this a government thing or is it third parties?
It's typically provided by FAA-approved third-party service providers. They're called USSs, or UTM service suppliers. They act as intermediaries, and they all share data through standardized digital APIs. It's a decentralized traffic management system. And strategic deconfliction is that first critical step. So before the flight, the operator submits their full 4D box, the route, altitude, time, to their USS. The USS then checks that plan against every other known UAS plan, any known manned traffic intent, TFRs, and special use airspace.
So if two different operators accidentally plan to use the same little piece of corridor at the same time and altitude,
the UTM system immediately flags it.
And it forces one or both to adjust their timing or their altitude before they even take off.
That's strategic separation. It removes probably 90% of the potential conflict before the drone ever even leaves the ground. But the real-time safety load during the flight, that's carried by detect and avoid, or DAA, and something called conformance monitoring.
Okay, let's dive into DAA, detect and avoid. This is the tech that has to replace the pilot's eyes. What specific components are we talking about for a Part 108 BVLOS operation?
DAA is almost always a complex system of multiple integrated sensors. It's really never just one thing. For high-reliability BVLOS, you'll often see a combination of, first, ADS-B in-out for tracking cooperative manned aircraft that have transponders.
Ones that are broadcasting their position.
Right. But you also need non-cooperative sensors, like small, lightweight airborne radar that's designed to see aircraft that are not transponding, like gliders or some smaller helicopters. And third, you often have electro-optical systems, cameras for visual verification or final close-in detection.
What's the major technical snag, the weak point in relying on this DAA system?
Well, there are three, really. Coverage gaps, latency, and the required range. So like we said, radar can miss things like gliders. Optical systems fail in low contrast like haze or sun glare. More critically, the required DAA range for a drone cruising at 100 knots needs to be long enough, we're talking several nautical miles, to give the drone enough time to execute a maneuver to avoid a fast-moving manned aircraft.
And all that data has to be processed instantly.
Instantly, with ultra-low latency. If the data arrives too late, the avoidance maneuver will also be too late. It's a race against time.
So while DAA is handling that immediate traffic threat, conformance monitoring is handling the route boundary threat. How does that work in real time?
Conformance monitoring is the digital watchdog. It's constantly tracking the drone's actual position, its telemetry data, against its approved 4D box. So if the drone drifts laterally out of its approved RNP corridor or violates the approved altitude band, alerts immediately fire in the control center.
Okay, let's tie this back to that AGL MSL trap we talked about. How does conformance monitoring prevent a shelf bust that's caused by rising terrain?
This is where those high-fidelity terrain models become critical during the flight, not just in planning. The UTM service, or maybe the internal flight controller, receives the drone's current GPS position and its barometric pressure reading.
Okay.
It then instantly cross-references that position with the preloaded digital elevation model to calculate the drone's exact MSL altitude, factoring in local atmospheric pressure.
So it's constantly calculating its true altitude above sea level.
Continuously. And this calculated MSL altitude is then constantly compared against the static MSL floor of that controlled airspace shelves. If the calculation shows the drone is approaching the shelf, say, it gets within 50 feet of the boundary, a non-conformance warning is immediately issued, or in a more advanced system, an automated procedure forces the drone down to restore that required separation margin.
Without that UTM and terrain integration, that MSL trap is basically unavoidable once you introduce hills and mountains.
It would be impossible to guarantee conformance for long corridors. Absolutely impossible. That's why UTM is a mandatory safety system for any kind of scalable BVLOS. And this need for robust DAA and UTM integration is particularly strict in high-density areas, specifically what's called the Mode C veil.
The Mode C.
That 30 nautical mile bubble around major airports.
So what specifically does a BVLOS drone have to do differently inside that veil?
Well, the Mode C veil is defined by extra rules. It extends from the surface all the way up to 10,000 feet MSL and is designed for high-density traffic. Inside this veil, the regulatory insistence on visibility is paramount. For manned aircraft, that means a mandatory Mode C transponder.
And for drones?
For BVLOS drones, it means facing significantly more stringent requirements. You'll likely see mandated ADS-B out or a functionally equivalent broadcast system, and often higher reliability standards for all your DAA components. Your corridor rules have to be tighter, your performance requirements higher, and your UTM integration has to be flawless.
Just because the consequences of a mistake are so much higher.
Exponentially higher. Regulators demand these structured corridors precisely to ensure we can have safe separation without completely overwhelming traditional air traffic control.
Okay, we've established the corridor is the contract, and the UTM DAA system is the enforcer. But even the best laid plans, they break. And this seems to be the heart of operational mastery in BVLOS, how you manage the surprises that invalidate your 4D box.
It is. The central realization here is that you've deliberately eliminated your easiest, most flexible sensor, the human eye. In VLOS, the pilot is constantly, almost subconsciously, performing non-cooperative target detection.
Just looking around.
Just looking around. In BVLOS, you are completely reliant on this complex system of systems. And if any part of that system fails, or if an external element changes, the surprise, The entire safety case can just unravel in seconds.
And the data fusion of those sensors, the radar, ADS-B, the optical, it has to be perfect to recreate the situational awareness the pilot lost.
It has to be. And the failure is so often rooted in latency. If your DAA system detects a fast-moving threat 20 seconds out, but it takes 15 seconds to process the data, transmit it to the ground, for the pilot to see the alert, make a decision, and then transmit the command back to the drone.
You only have 5 seconds left for the drone to even begin to maneuver.
Exactly. That's a critical safety margin issue. It's a huge problem.
Now, our sources break down these unexpected events into 4 main categories of surprise that can invalidate your corridor contract. Let's walk through the playbook for each one, starting with airspace surprises, like a pop-up TFR.
TFRs, temporary flight restrictions, are dynamic airspace changes. They can be generated instantly for things like wildfires, presidential movements, or major sporting events. And they have the authority to just clip or completely invalidate a pre-approved corridor segment with almost no notice.
Okay, give us a scenario.
Take an urban medical delivery corridor. It's operating under a major Class B shelf. Everything's planned for routine delivery. Then, 2 hours before a major playoff game, a TFR is activated, and it clips the final approach segment of your route.
And you can't just fly through it. Even if you have an active Part 108 certificate, the TFR trumps everything.
It overrides everything. Your corridor rights are gone. So the operator must have a pre-scripted contingency plan. They must execute a pre-approved alternate shell corridor.
Alternate shell corridor. What defines the shell part?
A shell corridor is essentially a pre-evaluated, geometrically buffered route that's designed to bypass the TFR. You might have to fly a longer, slightly lower path, maybe hugging a different set of infrastructure, but it's specifically designed with an extra buffer, the shell between your route and that new TFR boundary.
And if there isn't one?
If no pre-approved safe alternate is available, the mandate is immediate. All flights that intersect that TFR's time window have to be suspended. And any drone currently inbound must execute a controlled landing at a safe zone outside the TFR.
Okay, next up. Traffic surprises. This is when you get unexpected manned aircraft that didn't file a flight plan. Usually helicopters in low-altitude environments.
This is a massive threat in shielding corridors, especially those that follow linear features like rivers, canyons, or major highways. So consider a media inspection corridor that's following a major river at 200 feet AGL. A news helicopter, or maybe a medevac flight, responding to an incident, suddenly drops into that valley. They're flying low and fast, and they are entirely non-cooperative with your UTM system. Your DAA is your only immediate defense.
And we talked about the pre-scripted response for this. An immediate vertical descent to 100 feet AGL. Why is descending safer than, say, trying to maneuver horizontally or climb away?
It comes down to procedural separation and, really, the human factors of the manned aviation world. Manned pilots generally expect the airspace above 200 feet AGL to be relatively clear of hazards, but they are constantly aware of obstacles and wires below that height.
So they're already looking down.
They are. By executing an immediate vertical descent to, say, 75 feet AGL, the drone intentionally enters the most obstacle-rich, most shielded volume near the ground feature. This maximizes the procedural separation because that manned helicopter is highly, highly unlikely to be operating in that tight little volume.
You're essentially using the landscape as cover.
Precisely. You immediately move to the lowest safe zone, you reduce your speed, and you hold. The goal is to stabilize the situation and wait for the manned traffic to clear the area, relying on the sheer improbability of them following you down that low.
Okay, let's move on to system surprises, when the technology that governs the whole system fails. Specifically, a UTM outage. That sounds like a terrifying thought for scaled BVLOS.
It is the moment where your strategic safety just dissolves. If the UTM loses its heartbeat, the central coordination system fails. You instantly lose your strategic awareness of every other drone operator in that shared airspace. Your own internal DAA is still working, but you can't trust the broader picture anymore.
So what's the standard playbook when that happens?
The playbook is mandatory, and it's non-negotiable across most of the regulatory proposals we've seen. First, stop launching any new flights immediately. For any flights already in the air, there's typically a short grace period, often defined as about 5 minutes.
Just 5 minutes?
5 minutes. During which the drone continues on its path, relying solely on its localized DAA system. If the UTM heartbeat doesn't return within those 5 minutes, you must execute a controlled landing or hold in a predefined geographically isolated, safe loiter bubble until the service is restored.
That's a huge operational constraint, but I guess it's necessary because you've lost that digital trust layer that manages the entire corridor.
You've lost the ability to enforce the contract. And finally, infrastructure surprises. This is kind of a silent killer for corridor geometry, since it's a change on the ground that messes up the sky contract.
Give us the scenario for this one.
Okay, imagine you run a recurring automated highway inspection corridor at 200 feet AGL. It's perfectly optimized to maintain clearance from the Class E shelves above.
Yeah.
On flight number 50, the drone's obstacle avoidance system flags a brand new 300-foot construction crane or a cell tower that wasn't there the week before, and it's now sitting just 30 meters from your approved center line.
So the drone didn't enter controlled airspace, but the corridor's safety margins are just gone.
The corridor's assumed validity is broken. The proximity tolerance of your original Part 108 certificate is now violated. The drone has to immediately execute its obstacle avoidance protocol, descend and avoid and stabilize. But the operator's long-term response is what's paramount.
What do they have to do?
They have to permanently update the corridor model. They have to update their obstacle database with the new structure's height and coordinates, and then formally revise the safety case for that segment before any future flight can happen there. Failure to do that means you are operating outside the parameters of your approval.
This all seems to come together in the wildfire TFR scenario, which ties the shelves and surprises together in a really high-risk environment.
Wildfire environments are totally unique. The TFR itself is highly restrictive to general aviation. It creates a perimeter of no entry, but it's actually highly permissive if you are an approved emergency BVLOS operator. The TFR acts as this temporarily self-contained airspace, where the safety shelves are defined not by geographic class, but strictly by your role.
Tell us about that vertical segregation by role.
The procedures strictly define who operates where to prevent conflicts between all the different firefighting assets. So drones have to operate at the lowest altitudes, typically below 200 feet AGL. They're used for mapping, thermal sensing, or perimeter monitoring.
Okay.
Large manned aerial tankers, the ones dropping fire retardant, they need a clear, predictable path. They're often flying between 300 and 800 feet. And then manned helicopters are even higher still, acting as air attack supervisors or transporting personnel.
So the altitude separation is purely based on the job being done at that moment.
Exactly. And the critical rule is absolute and it is non-negotiable. When a tanker is inbound to make a drop, all drone operations must immediately cease forward movement, descend to the minimum safe altitude, we're talking 50 feet AGL or even lower, and then hold in their assigned loiter boxes until the air attack supervisor confirms the area is clear.
The manned traffic always wins.
The manned firefighting traffic always wins. There is zero tolerance for delay or non-conformance. This is the ultimate example of procedural control carrying the entire safety load.
So we've established that designing these BVLOS corridors isn't just about drawing lines on a map. It's really about drawing up a contract that anticipates and mitigates failure from the very beginning. This requires a shift to a kind of meta-level design philosophy.
That's the mastery layer, I think. Designers of these corridors have to be proactive risk engineers. They must explicitly bake in every single detail: the lateral width, any choke points, the altitude bands of both AGL and MSL, the relationship to the shelves, and specific pre-written plays for every single failure mode we've discussed.
So the philosophy has to be that you design the corridor in a way that surprises become rarer, smaller, and easier to handle.
Significantly easier to handle when they inevitably occur, yes.
So the designer is hunting for the failure points before the pilot ever even launches. But when a surprise does hit, the pilot is under severe cognitive load. They can't be inventing a response on the fly. They have to execute a rehearsed playbook. And our sources provide a great real-time framework for this, HRA.
The HRA playbook: hold, reroute, abort. This framework is so crucial because it gives the remote pilot an immediate three-step logic process to follow under stress. It prevents panic, and it prevents that deadly issue of mode confusion.
Let's break down the holdy step first. What does stabilize the situation actually entail?
Okay, so holdy is all about gaining time and data. The immediate, probably automated response should be to drop to the lowest safe AGL, move to the safest part of the corridor, so maximizing shielding if it's available, and then enter a stable loiter or a drift-suppressed flight mode and slow down.
Get predictable.
Exactly. Minimize your kinetic energy, reduce the footprint of the aircraft in the airspace, and just let the situation develop. If the surprise is a non-cooperative helicopter, descending and slowing stabilizes the drone in a predictable, low-consequence location.
Okay, so once you're stabilized, the pilot can assess the risk and move to the second step.
Second step is reroute. If the risk assessment shows that the threat is localized or temporary, like a blocked segment because of a micro TFR, the pilot can then use a pre-approved alternate path, a different altitude band, or even a different time slot.
But that alternate route has to already be part of the plan.
It must already be covered and certified by the original Part 108 safety case. Rerouting is a measured choice, not an invention.
And finally, abort.
Third step, abort. If the validity of that corridor and the minimum safety margin just cannot be guaranteed, say the UTM system fails permanently or the DAA system reports a persistent, unresolvable threat, the pilot must execute a controlled return to the nearest safe landing zone or back to the launch point.
And aborting is a safety success, not a mission failure.
That's a great way to put it. It is a safety success. It means the pilot followed protocol and refused to push risk when their data assurance was lost.
This level of discipline requires a really specific pre-flight mindset, what we're calling hunting the failure.
Hunting the failure is, I think, the single most valuable BVLOS habit a pilot can develop. It moves the remote pilot's job from just flying a route to proactively managing risk. Before launching, the remote pilot needs to mentally rehearse the failure modes against the specific corridor segment they're about to fly. It's like a mandatory what-if checklist.
So what are the absolute high-priority what-if checks that every BVLOS pilot should run through?
Well, the checks have to focus on the worst-case scenarios and how the automation is going to respond. So you have to ask, if my command and control link dies right here over this steep terrain, then what? Is the automated return to home path compatible with the shelves and the ground risk?
Because the default RPH might be to just climb straight up.
Exactly. Many RTH systems are programmed to climb straight up to a high altitude to try and regain the link, a protocol that could instantly punch you through a Class B shelf. You have to confirm the RTH altitude respects the MSL ceiling.
Okay, what else?
Second, if UTM drops while I'm in this shared airspace segment, then what? Do I have 5 minutes of grace, and where's my nearest safe loiter bubble? And third, what if my highest confidence sensor, my forward radar, fails right as I enter the Mode C veil? Do I immediately execute an abort, or can my secondary electro-optical system carry the DAA load?
This practice really primes the pilot's brain so that when the surprise does come, it's instantly recognized as, this one, and it prevents that moment of panic or mode confusion that leads to errors.
Exactly. And this mindset is so crucial because BVLOS completely changes the role of the human operator. You are no longer flying an aircraft. You are supervising a highly complex, safety-critical system.
And the human factors research consistently highlights that in these automated supervision roles, workload spikes and mode confusion are major, major risks. The pilot needs to be a manager, not a manual flyer.
Yes. They're monitoring multiple data streams at once: telemetry, DAA, UTM, weather. When an alert hits, they have to instantly transition from being a passive supervisor to an active decision maker. And if the system gives conflicting alerts, say, DAA says descend to avoid a helicopter, but the RTH logic says climb to regain the link, the pilot has to know which automated boundary must never ever be crossed.
Which means those automation boundaries, what the drone may never do by itself, have to be ironclad. They have to be explicitly programmed based on that corridor contract.
They have to be strict and explicit, dictated by the Part 108 safety case. The autopilot may never climb above a certain MSL altitude or exit the shielding volume laterally by more than, say, 10 meters, even in a lost link scenario. This prevents the automation from making a choice that is logically sound for the drone itself, like regaining link, but is disastrous for the broader airspace picture, like popping through a Class B shelf. You need powerful automation, but it has to be clearly fenced within the limits of that human-signed regulatory safety contract. #tag outro. So to try and synthesize this really complex discussion for you, the learner, we have 5 non-negotiable points that I think define mastery in this BVLOS airspace environment.
Let's hear them.
1. Corridors are contracts, not convenience. They require absolute adherence to standardized RMP performance requirements and specific failure playbooks, all dictated by your Part 108 permit or certificate. 2. Shelves are sneaky. Never ever rely on AGL alone. Always check your MSL altitude against the MSL-defined controlled airspace floors and design your corridors with explicit safety margins against that terrain rise, the stacked bricks of Skytrap.
Right.
3. Shielded operations are central to low-risk BVLOS deployment. Hugging infrastructure drastically lowers the acceptable level of risk, the ALR, by creating a self-separating volume that unlocks those long-distance routes.
Makes sense.
4. UTM and conformance monitoring are mandatory safety systems. They provide the strategic deconfliction before the flight and the real-time MSL terrain checks during the flight that have to replace the visual presence of the pilot.
Yeah.
And 5, below 400 feet is not a magic shield. You must still respect all airspace classes, all TFRs, mode CVALs, and local shelves. Mastery requires viewing the low-altitude sky as highly structured, not uncontrolled.
That is a phenomenal, actionable summary. It really highlights how BVLOS mastery requires thinking like an aviation systems designer and a risk engineer, not just a pilot flying a machine.
That's the shift.
So, as we wrap up this deep dive, we want to leave you with one final thought building on all this material. What does this fundamental shift from operators arguing for custom exceptions via waivers under Part 107 to now plugging into standardized corridor templates and certificate programs under Part 108? What does that imply for the pace of innovation in drone delivery, inspection, and logistics over the next decade? Does this necessary standardization enable the massive scale of automation we've all been waiting for, or does it risk stifling the kind of rapid, out-of-the-box thinking that defined the drone industry's early, often chaotic years? Something to mull over until our next deep dive. That's a wrap on today's mission, Commander. See above, go beyond, get ahead. For more training, tools, and intel, head to skycommander.ca. If you learned something new, share it, subscribe, and leave us a 5-star debrief.